Welcome, everyone. Today's Charles River hosted webinar is titled Using Fine Motor Kinematic and Gait Analysis in Vivo Pharmacology Studies, a sensitive method to detect drug-induced motor impairment. Our presenters for today are Timo Brahe. Timo is a primary scientist involved in complex big data analysis and kinematic gait analysis at Charles River. He uses advanced mathematical and statistical tools to evaluate in vivo data across various CNS disease models and assays. Timo's academic background includes a master's degree in medical physics. Our second presenter for today is Tinelli Heikkinen. Dr. Heikkinen is a senior scientist and team leader specializing in the area of neurodegenerative diseases, including Huntington's disease, ALS, and Parkinson's disease. He has academic training in neuroscience from the University of Eastern Finland and has authored multiple peer-reviewed publications. It is now my pleasure to turn things over to our presenters and begin today's session. Please go ahead, Timo.
Thank you, Megan. Here's outline of this presentation on kinematic gait analysis. First, we go through the background and methods. Second, we will take a look at few case studies with different rodent models. And let's first talk about the background and methods of kinematic gait analysis. What is kinematic gait analysis? Let's begin with the kinematics first. So, generally speaking, the kinematic analysis is the process of measuring the positions or velocities of an object to describe its motion or movements. Gait is the most common movement activity both in humans as in animals. And animals with four limbs use a variety of different gaits at various speeds, from slower walk to faster trot and gallops. So, kinematic gait analysis can be defined as the systematic and quantitative study of animal locomotion, and the aim is to measure the motions of underlying bones and movements of each joint. One widely used kinematic analysis process is called marker-based motion capture. So that's something we are doing here. And here on the right-hand side, you can see a mouse with marked anatomical landmarks with different colors. And those markers are tracked. And on the bottom is an example of kinematic model or snapshot of the reconstructed motion. And finally, from the kinematic gait model, several parameters describing various gait properties can be automatically determined. As you all know, patients suffering from human CNS diseases such as stroke have impairments in their ability to move, as well as in tasks requiring accuracy and coordination. And that's why kinematic analysis is widely used in human patients for diagnostics and monitoring the effects of therapy. Different preclinical rodent models for diseases with motor impairments manifest similar kind of symptoms as humans. Fine motor kinematic analysis can be used for several applications. We have experience from different rodent injury models, such as stroke and spinal cord injury, and also different genetically modified mouse disease models, such as Huntington's disease and ALS. Importantly, this tool provides sensitivity to study the efficacy testing of treatment and also possible side effects. Kinematic analysis can also be used for phenotypic type characterization of various strains of rats or mice and for longitudinal evaluation of disease progression. And now here we briefly describe our methods. On the left side, you can see images of a mouse walking in the alley of the motorator apparatus. And the images are recorded with high-speed camera simultaneously from left and right side of the mouse, as well as from the bottom. And full body tracking can be done using 31 markers, reflecting movements of all major body parts of the animal. In addition to normal gait analysis, the system enables also analysis of ladder walking, wading, and swimming. So in these cases, there are water involved. On the right side, you can see a hind limb skeleton and different joints marked and tracked over a complete gait cycle. Let's talk about the kinematic gait parameters. The gait is cyclic process of repetitive strides or gait cycles. In our analysis, a full gait cycle is defined as the period between two consecutive left hind limb floor contacts. And for each automatically detected gait cycle, a large number of parameters are determined to characterize the gait properties. First, the spatiotemporal parameters measure overall stride distance, duration, and speed. And the gait cycle is typically divided into two phases. The stance phase, that's when the limb is in ground contact, and then the swing phase, when the limb moves. Okay, when we know the exact timing of each limb, then the inter-limb coordination can be assessed. So you can imagine if you have 4 limbs available, there are plenty of different gait strategies available. These parameters characterize the gait pattern and rhythm, such as diagonal or trot-like gait. The swing phase parameters measure pause speed and also several fine motor properties of the gait. So there are questions: how smoothly the limb moves, or what kind of shape the trajectory has, or is there any excess or abnormal movements during the swing phase. So we have several parameters describing that kind of things. Then we have several parameters describing body posture and limb function. For example, hip height, tail movements, joint angles, and also detailed head movement. The gait varies from stride to stride within an individual, and usually this kind of variability is small in healthy subjects, but not in animals with motor impairments. Therefore, we also measure this variability, such as deviations in the step width, or among other parameters. So now we have data over 100 gait parameters, and the problem is how to handle all this information. So it's known that many, if not all, gait parameters correlate somehow. For example, shorter stride duration and longer step length, and that leads to higher speed. Or if the hip height is very low, then the knees have to be flexed. How can we see the big picture through all the individual parameters, and how can we identify higher level gait features? A good approach is the use of principal component analysis. So this is a powerful multivariate statistical tool to first compact the information, to identify correlation between original variables, and ultimately to create a small set of new and more sensitive uncorrelated parameters. Those are called principal components, or PCs. And here on the right hand side, you can see the heat map, which consists of 10 principal components, and the rows correspond to individual parameters. They are listed here, quite small font, but yes. In this visualization, we can see the 10 most common gait features in this example dataset. Each column represents a PC, a gait feature consisting of parameters which do correlate together. And in this heat map, red means positive correlation and blue negative. Black means no correlation at all. So if we take a look at the first column, we see red color here. It's quite dull, but it's red at stride distance and also peak swing speed, and blue color at stride time here. So this means that longer steps, higher swing speed, and shorter stride time are correlating. That's logical. If we walk faster, you increase step frequency and take longer steps, or both. This first PC can be interpreted as overall speed, for example. In the same manner, we look at PC5, so it's there. This can be called as tail tip height, and PC7 as overall hip height, which consists of both tail base and also hip height parameters. PCA captures every time those gait features which are the most common in the current dataset. When the original data is transformed using the PCs, we get the PCA results, PC scores. And here on the small figure, we see an example of 3 PC scores from one study, shown as group means and standard error. Okay, in the previous slide, we managed to condense our 100 parameters into 10 PCs. And here we introduce a PCA-based overall gait analysis score, which further compacts the information and also characterizes the disease model. First, the score is based on differences between healthy control group and the disease model group. The aim here is to identify such a fingerprint or combination of original variables which characterizes the disease model in best possible way and differentiates the 2 groups. Here on the upper right corner, we see PC scores of 3 first PCs from one study. And here the blue arrows illustrate the difference between the transgenic and control group in each PC. Now, the individual PCs are emphasized based on these differences, and corresponding gait features are collected in the single discriminant vector, shown here in the middle. The discriminant vector bar graph illustrates which parameters altogether characterize the disease model. And the bar length and direction shows how the disease model differs from the control. For example, here we have the increase in knee angle range and decrease in minimum knee angle, or here is an highlighted example. So we can see that the transgenic mice differ. That's why, or that's how, from the wild type. And overall, we can call this discriminant vector as a kinematic fingerprint of the model. So one glimpse and we see everything what's happening in kinematical parameters. Finally, the overall gait analysis score for each individual mouse can be now computed using the discriminant vector, and it's shown on lower right. Now, the score consists of all of those parameters which characterize the disease model. And ultimately, the overall kinematic effects of a pharmacological agent can be seen in highly sensitive manner with a wide therapeutic window. And that's all from me. So now I give talk to Taneli about the case.
Thank you, Timo. Now here we will present a few example studies with this method. Before defining the specific features of gait of a disease model, we need to understand the gait properties of a normal healthy animal. Thereafter, we used a PCA-based approach that enables the identification of kinematic fingerprint, meaning the combination of original parameters which best differentiates the disease model group from the control group. In order to have a reasonable disease model for pharmacological research, there has to be a sufficient therapeutic window. In addition, it is essential to have an understanding of the time course and magnitude of the kinematic changes in the model, as well as the properties of the pharmacological treatment used. Here are presented examples of kinematic gait of a 5-month-old wild-type mouse and an MDX mouse, a genetically modified mouse model of Duchenne muscular dystrophy disease. These videos are constructed from data analyzed from the actual video recording, the green line being the tail, and red lines the right limbs, and the blue lines the left limbs, and the green spot being the nose. Clearly, the MDX mice have altered gait compared to the wild type. Obviously, the overall speed is lower, but are there any changes in the kinematic gait pattern? As revealed by the kinematic gait analysis, the MDX mouse shows strong alterations in lower body posture, which can be seen in increased hip height, increased hip, knee, and ankle extensions, and also in increased overall hip height and decreased forelimb toe clearance compared to the wild-type mice, shown here in these bars. These kinematic fingerprints, the discriminant vector of an MDX mouse is shown right, with the mentioned most distinct alterations encircled red. In the far right panel, 3 separate parameters are shown as examples: hip range of motion, hip height, and forelimb toe clearance. The overall distance from wild-type score, shown on the left panel, completely separates the genotypes. Here are shown characteristic examples of gait cycles of 10-week-old wild-type mice on the top and R62 mice of Huntington's disease below. At this age, the gait of the R62 mice is clearly disrupted, and if you look at closely, you may see an abnormal, modest, shaky movement in the front paw of the R62 mouse. As can be seen in the discriminant vector in the middle panel, at 10 weeks of age, most pronounced changes of R62 mice are disturbed interlimb coordination, shorter strides, and protraction and retraction shifted to forward direction. Interestingly, for some of the features, such as the forelimb trajectory profiles, can be seen at the early age of 4 weeks, but not as strongly at 10 weeks. These are indicative of abnormal features in the gait that are specifically present only in the very early age. The overall discriminant vector scores that are shown on the right show highly significant genotype difference already at the early age of 4 weeks. Then here we present a few pairs of individual parameters which show very characteristic changes in the R62 mice. And there appears to be a link between the 2 parameters. Lower tail and back body posture during gait can be observed already at 4 weeks of age. Proportion of diagonal cadence as well as stride distance decrease as the mice age. As the hind limb retraction, extension to backward direction decreases, at the same time protraction, extension to forward direction increases. Notably, increased protraction can be seen at 4 weeks already. Together, the changes in these parameters are partially implicated with the lowered back body posture. The subtle, shaky, scrabbling-like front paw movements that were visible in the presented video are very unique to the R62 mice and can be objectively captured with kinematic fine motor analysis. The parameters on the right describe namely these changes as excess paw movement both in horizontal and vertical direction during swing phase. Here we then present part of published data with beneficial treatment effects on fine motor and gait kinematics in 10-week-old R62 mice. The overall discriminant vector score on the left shows clear genotype difference and also beneficial treatment effects. On the right are presented a few individual parameters with significant genotype and treatment effects. Affected individual parameters were, for example, in the upper row, stride distance, a mean, and maximal speed. In the middle row are shown parameters describing 2 different forms of ground support and the length of forepaw trajectory during the swing phase. On the bottom row are depicted retraction and nose height, both of which were well restored close to the wild-type level after the treatment. These data are from SOD1 mice modeling ALS, having 2 measured time points, 11 and 16 weeks of age. The overall discriminant vector score on the left panel shows clear difference between the genotypes at both times. The median disease onset of these mice is very close to the 16 weeks age point. So at that point, roughly half of the mice have already developed notable defects, and the other half not so much. That's why the variation within SOD1 mice at 16 weeks of age is somewhat large. A few early features of the phenotype are shown on the right, having lower tail tip and decreased hind leg protraction already at 11 weeks of age. Also, the range of motion of the knee joint has started to decrease at this age. In the kinematic fingerprints can be seen that, interestingly, the back body posture of SOD1 mice is elevated at 11 weeks, but lowered at 5 weeks later, shown here. Here is presented another model of CNS disease, a Cuprizon-induced model of MS. As a naive mouse in the upper video walks smoothly, there are clear deficits in the gait of the Cuprizon-treated mouse in the bottom. These measurements were performed 6 weeks after the Cuprizon treatment. The kinematic analysis reveals a few major factors describing the gait features of the Cuprizon-treated mice. These can be seen on the right panel. The gait is characterized by slower overall speed, these parameters here and here also, shorter stride distance, less diagonal or trot-like gait pattern, and excess tail tip movement, shown here. In addition, the tail has more ground contact and the nose height of the mice is decreased. And again, the overall discriminant vector score on the left shows clear difference between the groups. On another note, in this study with the same mice, we performed also DTI imaging analysis. In a further analysis, we found that, interestingly, white matter-rich regions in corpus callosum correlate with multiple parameters in the kinematic analysis. Together, these build a bridge between the structural and functional changes in this model. In a different kind of approach, we wanted to evaluate if and how psychoactive drugs affect the fine motor capabilities and the gait of the mice. For that purpose, we examined the acute effects of diazepam, amphetamine, and morphine. The upper video shows the gait of a vehicle-treated mouse, and the video in the bottom, a diazepam-treated mouse. By looking at the videos, it seems that there are no very dramatic differences in the gait other than the somewhat slower movement by diazepam. Similarly, as looking by eye, amphetamine doesn't seem to have very big effects on gait, whereas morphine induces very distinctive tail positioning in the mice, as shown in the lower video. And here are summarized the kinematic fingerprints of these pharmacological treatments. Even though, as looking at the videos, the gait didn't appear to be dramatically altered with diazepam or amphetamine treatment, the kinematic analysis was able to identify very clear patterns of movement. For diazepam, the kinematic fingerprint can be described as decreased speed, these parameters here, decreased nose height, altered trajectory profiles, and excess forelimb vertical movements. And for amphetamine, as higher overall speed, as well as elevated hip and tail tip height. As observed, for morphine, the most prominent feature was the extremely elevated tail. However, kinematic analysis shows also decreased retraction and protraction, increased hip height, and decreased speed. Here we show the data of a rat model of stroke. Here the male Sprague-Dawley rats were subjected to 90-minute transient middle cerebral artery occlusion. Then the rats were measured on days 14, 28, and 41 after the occlusion. Disease model-related changes can be seen in several parameters, yet significantly in a number of individual parameters, shown on the right. Most notable parameters characterizing the model are decreased knee and ankle angles and ranges, and protraction, retraction in backward direction. However, when the information of all kinematic parameters together are taken into account, the differentiation between naive and TMCAO rats is quite nice, as seen in the distance from naive figure bottom left. And lastly, we present a neuritis model in rats. This is a model that provides a combination of sciatic nerve inflammation and neuropathic pain. Rats undergo surgery for placement of CFA-soaked matrix adjacent to sciatic nerve on the left side. Here we studied the effects of acute gabapentin treatment and measured the rats on days 3 and 7 after the operation. Typical readout or measure in neuritis model is tactile and thermal allodynia, which show also reversal by commonly used treatments like gabapentin by alleviating allodynia responses. In this case, by kinematic analysis, neuritis group demonstrated, for example, faster speed, elevated hip height, and lower falling trajectory profile. However, due to nature of unilateral model, the left and right side differed in many ways. For example, the peak speed of the hind limb, here in the middle, was increased on day 3 on the right, but not on the left side. Gabapentin had an effect to overall speed and several parameters describing fine motor function, such as trajectory profiles, nose and tail tip movements. Although not shown here, tactile and thermal allodynia was significantly reversed in gabapentin-treated group. To summarize, the fine motor kinematic analysis method offers a tool to investigate detailed gait properties and subtle yet highly significant changes in rodent models with motor deficits. It produces up to 100 individual parameters of different aspects of gait and fine motor movements. Further, the principal component analysis reveals correlations between individual parameters, providing a comprehensive overall view on the movement patterns. Given the automated analysis method, it is objective compared to, for example, test assays that depend on subjective scoring. With the sensitivity, it also provides a wide therapeutic window for possible treatment candidates. Thank you.
Thank you, Timo and Tonelli, for a great presentation. We will now move on to the question and answer portion of today's webinar. The first question that we have is, would there be any other way to analyze the data besides the parameter-based analysis?
Yeah, that's quite interesting question. Yeah, we have used parameters, but it's also possible to do kinematic analysis based on trajectory data itself. And I have seen a couple of studies where that has been done in humans in some sport applications, and I think that's something quite interesting and also might be quite beneficial to try also in animal models, because when we have a set of parameters, even though we have 100 parameters, these still capture only a portion of all possible information which is in the video or the marker trajectory. So when and if we would use all the trajectory data, that should be even more sensitive than the current methods.
Thank you. We have another question. Do you have positive control data from the MDX mice, perhaps from the FLASA court? The next question I have is, does this assay require animal training?
Usually, the animals do their best runs, actually from 1 to 5 runs in a row. We have when we validated this, we we of course tried many different combinations, training the mice and rats over weeks and so, but eventually we found that they had the best motivation to run through the brightly illuminated corridor in a very few runs.
The next question we have is, how many steps are required for the rodent to take to enable analysis? What do you do if the rodent doesn't want to move across the platform?
Yeah, the first part, how many steps? Of course, in statistical point of view, more is better. And our guidance is to analyze at least 6 gait cycles. So that's the quite reasonable minimum. And of course, sometimes the animal don't move, so then we need to record several recordings and try to somehow lure the animal to move.
The next question we have is, how long does it take to run an assay and analyze the data?
Well, of course, it depends on how large the animal number is and so, but basically, I would say with a normal cohort of, usually we may have just 10 or 20 mice, 10 or 12 mice or rats per group to get significant or statistical power with the group. So if we have, for example, 4 or 5 of those, so I would say in a few weeks or so we get all done, including the analysis.
Okay, great. Thank you. So with that, I will conclude today's webinar. We will include contact information in the follow-up email that is sent, so you can contact us directly with your questions. You may also contact us using the phone number on your screen or via email at askcharlesriver@crl.com. You can always visit our website for additional information as well. I would like to thank our presenters for their presentation, and we want to thank all of you for attending. Have a great day, everyone.